Hi, here we are discussing about the algorithm present, an ultra lightweight block cipher. So here the present cipher is an ultra lightweight block cipher designed specifically for environment where resource constraints are critical, such as the RFID tags, sensor networks and various IoT devices. So it's a compact design with a 64-bit block size, 80-bit key and 31 rounds make it particularly well suited for applications requiring minimal hardware resources, low power consumptions and moderate security. Unlike more robust ciphers like AES, which demand significant computational and memory resources, Presence offers an optimal balance between efficiency and security for constrained devices. So this paper examines the practical applications for the present cipher in secure communications protocol, device authentications and data encryptions and for low power systems. By synthesizing 16-bit, 32-bit and 64-bit implementations on Xilinx Vertex 5 FPGA, so we show the cipher adaptability across various use cases, analyzing a key performance metrics such as area, delay and power consumptions. Our findings suggest the presence is highly effective in scenarios where traditional cryptography solutions are too resource intensive, so providing a viable alternative for securing data in a preserved computing environment. The Cipher applications extend to secure communications in embedded systems, protecting sensitive information in contactless payment method and enabling secure data transmissions in wireless sensor network. Now we can verify the paper. So this paper is fully designed for the present architecture of lightweight block cipher. So here the existing work of this paper, it may be compared with the previous algorithm of AES, E-stream and DES, okay, SHA algorithm, okay, so this kind of things. So here the top level algorithm descriptions of the presence, it will be given. Okay, so here the presence architectures come with the plain text, S-box layer and P layer. So compared to the previous algorithm of the AES and DES, example the AES for block size of 128-bit, it will be take the key size equal to 128, 192, 256-bit and number of rounds also it will be take 10, 12, 14. Okay, so here the DES also it will be take a 64-bit block size, key size it will be occupied 56-bit and 16 rounds. Okay, so here the presence of occupied only 64-bit with 80 bits of key size and 31 rounds it will be taken. Okay, so here the presence is considered as a lightweight because it strikes a balance between a security and resource efficiency, so that is optimized for small lower power devices. So while AES provide a stronger security and DES out data in the terms of security, so the presence excels in an environment where hardware resources are limited, so making it suitable choice for rapidly growing field of IoT and embedded systems. Okay, so here the present it will be additionally having a permutations layer. Okay, so here the S-box layer and P layer. So the P layer is a permutations layer. So this layer is fully focused for vital role in ensuring that the cipher achieves a strong diffusion. So while it's essential for security, it's effectively scattered the output of the S-box layer across the state, so complicating some potential attack vectors and making the cipher robust against the various forms of the cryptanalysis. So additionally, the simplicity and efficiency of the permutations layer align with a lightweight designs the goal of the present cipher, making it suitable for the implementations in resource constrained environment like IoT devices. The next method of architectures, it will be present with the S-box layer descriptions. Okay, so here this S-box, it will be come up with figure 2. It's having a multiple instance of S-box represented the S blocks in the diagram. So each S box is a non-linear subtraction functions that takes a 4 input and produce a 4 output. The S-box is applied 16 times in parallel for 64-bit state. So here the entire 64-bit block is divided into the 16 group of 4-bit, each of which is proceed with a separate S-box. So here the permutations layers also included. After the S-box layer, the output of the S-box is fed into the permutations layers with rearrange the bits of the entire 64 state according to the fixed permutations layer. The pattern is designed to spread the output bit from each S box across the different S box in the next round. And the SP network. Okay, so here the SP network, the combinations of the S box layer and the permutations layer create a SP network. This SP network is a core of the present cipher encryption process, and each round of the encryptions consists of an S box substitutions are followed by n permutations. The repeated applications of this SP network over multiple rounds provide a necessary complexity and security, and the overall encryption flow of this works starting from the input. The data is first substituted using S box, the permitted, and the finally paused on the next round of the cipher. So this process is repeated for all around 31 rounds in standard present cipher architecture. So here this work we have developed in Verilog HDL with support of 16-bit and 32-bit and 64-bit present architecture for IoT device applications and low power applications. Okay, and we have synthesized this work in Silence Vertex 5 FPGA and compared all the parameters in terms of area, delay and power. Now we can verify the Verilog HDL coding. Okay, so here this is a Verilog HDL coding for 16-bit architecture, and this one is a 32-bit and this one is a 64-bit, and simulation results. Okay, so this one come up with 16-bit. Okay, plain text. Okay, so this is a plain text and key input and cipher text. Okay, so here the each cipher we have generated. Okay, so here the different key also we have generated with for each cipher. Okay, so we can fix it with any key for all the inputs, or we can variable key also we can possible to use. Here this one come with the 32-bit. Okay, so it's also same. Okay, but the bit size will be increases and number of rounds will be increases. Okay, and this is a 64-bit plain text. Okay, so here we can vary number of bit analysis. Okay, so here you can check. So all the data will be encrypted, and it will be provide the results in the ciphertext. Okay, so here this work we have synthesized in Vertex 5 FPGA. So this is a 16-bit architectures. Okay, so this is a LED. Okay, and this is 32-bit and this one is a 64-bit. Okay, so here this comparisons we have updated in the comparisons table. Okay, so here the 16-bit encoder, 32-bit encoder and 64-bit encoder. So key size differentiate with 20-bit and 40-bit and 80-bit, and number of rounds present with 7 and 15 and 31, and the number of slice registers, LUTs, occupier sizes, IOB, delay and power we are compared. Okay, so this is a comparisons analysis chart. Okay, and for this project we have written abstract document. So proposed abstract, objective of this project. Okay, advantages and disadvantages and introductions with the related notes. Okay, and finally come up with literature survey. Okay, and references. Okay, thank you.